Hello everyone, hope you guys are doing really good. Today we will take a different route, and that will be to start with an example, and this example will be of a higher order system. We'll try to see how it is modeled, how it is plotted on an S-plane, and how it is solved to give us the response of the system in time domain. And in this whole process, the idea is to discuss different theoretical aspects as well, but obviously within the context of the example. And this will give us certain tools to analyze the previous discussions and connect them together, just like block diagrams connected with the transfer function and transfer functions connected with the differential equations. We'll try to make those connections as well along the way. So let's start the journey. So the example that we have chosen for this whole activity is that of a three-tank system. As the name suggests, that you're going to find three tanks in it. But how these tanks are connected together, let's pictorially show that. So the very first tank is going to look somewhat of this shape. There is an input coming in through a pipe, and you can label this to be Qi, which tries to fill this tank up. So internally you are going to find certain level of liquid that is going to have a specific height associated with it. Let it be like H1. The subscript 1 is indicating that it corresponds to tank number 1. And obviously the shape of the tank is also suggesting that there is going to be a constant area or exposed area. Let it be like A1. And I'm going to label that to be a constant. Now, out from this tank, from this opening over here, the fluid tries to get out, but there is a valve placed over here. And this valve is going to allow you to control how you're going to take the fluid out from the system. So this can be Q, let it be like QA, which gets into another tank. And I'm going to draw that tank somewhat different from the upper tank. So let it be like area A2 is a bit wider or a bit bigger than the area A1. So this is going to be having an exposed area, and obviously this area is A2, but it will also be constant because of the uniform cross section of the tank. But the height of the fluid in this is going to take a different value like H2. Now what does that mean? It means that you have fluid coming in from tank number 1 into tank number 2, and this tank from this opening over here tries to push the fluid out from it, and that would look somewhat like this. Like let it be like QB, indicated like a flow coming out of this particular tank. So then you have the third tank, as we have suggested that you have a three-tank system. So let it be like even a wider tank over here. So this is going to have a specific area A3, and the height of the fluid is going to be H3, obviously. And then from out of this tank number 3, you're going to have a valve, and which pushes the fluid in a controlled fashion out of it, and let it be like Q out, which we are interested in. So in this particular arrangement, you can see that you have tank number 1 over here, tank number 2, and tank number 3, all connected together in a specific arrangement. And you can see that you have valves out from these tanks, and these valves are going to have some resistance, obviously. Let it be like a resistance R, and in order to make it a more standardized version, I'm going to keep this R constant throughout. So it means that you have the same kind of valve placed out on these tanks. So we're going to try to explore this particular system. We'll try to see how things are constructed and how the mathematical model can be built, and we'll try to solve it as well. So let's start the journey. But before we start this journey, I can safely say that this kind of three-tank system can be widely observed in process industry. But I will give a little twist over here. I'll say that I'll refer to history of technology, and I'll try to find one very old example which can look somewhat similar to this three-tank system. Let it be like this. Over here you can see some 11th century old uh, depiction where you have a musical band, and this musical band is all automatons, and these automatons are being governed or being run by a cam follower mechanism over here. But internally the arrangement of this cam follower mechanism would require this camshaft to be rotated, and that is only possible if the fluid from this tank passes through in a controlled fashion into this tank, and from this second tank out into the third tank, and then in a controlled fashion over this uh, wheel, which is going to force this camshaft to rotate. So in that particular arrangement, you have tank number 1, tank number 2, and tank number 3 all connected together in a very careful fashion, which allows a specific kind of rotation over here, which forces these automatons to play a specific tune. And this particular depiction is made by a very famous engineer called Al-Jazari, and this is 11th century old. So it is very interesting example to start with. And this concept of uh, shifting the fluid from one tank to the other is called hydraulic switching. Obviously, there was no electricity back then, and they wanted to have somewhat a mechanism which allows a very uh, the switching action to be done in a very controlled fashion, and they used the specific size of the opening uh, out of a tank to perfectly mirror the timing of the switching. So in this particular arrangement, the concept of hydraulic switching is being used, and this concept is forcing this camshaft to rotate at a specific speed, which allows these automatons to play the specific tune. And obviously, interestingly, this camshaft is going to have different kinds of cams mounted on it, which is going to force these musical automatons to play different tunes if required. So this is kind of earlier example of programmable automatons, which is going to be very interesting for you to get into and observe how it is done. But we're more focused on how these three tanks are connected together. So within this context, we will try to see how it goes. So for tank number 1, you can see that there are two elements in it. One, which is the storage element corresponding to the fluid, which is capacitive in nature, and the other one is the valve over here, which is resistive element having a resistance R. So I'm going to have these two elements listed over here, capacitive and the resistive element. So for the capacitive element, I can recall that was something like the flow being fed to the system, like Qi minus the flow coming out from the tank, which is Qa in this case, to be equal to, since the area is constant, so that is going to be A1 times time rate of change of the height of the liquid inside that, which is H1. So this is the constitutive expression for capacitive element. And for the resistive element, which is valve, I can make you recall that was something like rho g h. In this case, this is H1, to be equal to the flow which is coming out from the valve, which is Qa times the resistance R. So these are the two constitutive expressions corresponding to tank number 1. We will use these expressions later on to construct the system response or system model. Similarly, I can write these expressions for tank number 2, And you can see that over here you have the flow coming in, filling this tank up. So this is going to be a capacitive element, and then you have a resistive element R placed over here. So obviously in a similar fashion you're going to have these two elements in that as well. So for tank number 2 you have the capacitive element to be something like this, that you have QA getting into the system minus QB to be equal to the different area A2 times time rate of change of height in the tank H2. So this is one of the expressions. The second expression is obviously for the resistive element. This is going to be in a similar fashion rho G. Now you have H2 to be equal to the flow coming out from the system, which is QB times the resistance R. Similarly, for tank 3, you can write these two expressions once again. I'll quickly do that. So for capacitive element, you have QB minus Q out to be equal to area A3. Then you have time rate of change of H3. And for the resistive element, you have rho G H3 to be equal to Q out times R. So these are going to be the expressions which we will use to construct the transfer function and observe how poles are placed on the S-plane. So we will try to build those in the next slide. Now remember, what is the task? Task is to find out the system's mathematical model. Now at this particular stage, you can see that you have these equations available with you, which you're going to use over here, and then using these equations in the third tank. And then in order to have the nth order differential equations, you define the system like this, where you provide the input, like in this case it is the Qi, and you get the output from the system, which is in this case Q out. So for that particular arrangement, what you need to do is to go through kind of a laborious arrangement where you can use the equations for tank number 1 into tank number 2, and from there into tank number 3 to construct the nth order differential equation. That would be laborious, obviously, but I'm going to raise this question that can we do some sort of an alternate route? Can we use the possibly the systems representation schemes that we have introduced earlier, just like block diagrams, and construct these models in a much more easy fashion? Can we do that? Yes, we can do that, and this is how we're going to do it. Schematically, this easy route would be a block diagram. And in this block diagram, what you have to do is to provide this input like a signal to first of the blocks. So the very first block corresponds to tank number 1. Now in this particular scenario, the Qi, which is given to tank number 1, is needed to be Laplace transformed to be used over here. So I'm going to use a capital letter for that. So this is going to be Qi for that matter. Now the output from this tank block T1 is going to be provided to tank number 2. That would also be represented like a block as well, and that would correspond to the transfer function of tank 2. The output from tank number 2 is going to be provided to another block in a similar fashion for tank number 3 as well. And the output from tank number 3 is obviously the output from the system, which is in capital letters like Q out. Now I can write down the intermediate variables as well. So this is over here between T1 and T2 QA, and between T2 and T3 it is going to be QB. Now what I'm going to do now is that how can I make use of these constitutive elements or expressions to construct the transfer function for tank 1. How can I use these two equations to construct the transfer function for tank 2, and how I'm going to use these two expressions to coin or construct the transfer function for tank 3. So this is going to be the task which I'm going to do in a moment. But before that, you have to realize that how these three different blocks are structured together to give you an alternate and easy route avoiding constructing the nth order differential equation. So all you have to do now is to make use of these two equations to construct the transfer function over here, these two for this block and these two for this block. So the very first expression that I require corresponds to tank T1, and that would be a transfer function placed inside this block. So let's quickly do that, and for that I'm going to make use of the expressions that we have already listed. So the very first expression that I'm going to make use is this, and I'm going to take the Laplace transform of that. So when I do that, this is going to be Qi of s minus Qa of s, and then you have equal to A1 s times H1 of s. And I should also re-emphasize once again that the necessary condition for the transfer functions is to use the zero initial conditions. So that's why this is going to be the expression for that. And similarly, I can take the Laplace transform of the second expression, and that would give me this expression that you have rho g h1 of s to be equal to qa of s times r. Now, since you know that in the expression over here, I need to eliminate this h1 of s, so that's why I'm going to kind of manipulate the lower expression. So this would mean that you can write down the expression for h1 of s, and that would be equal to r over rho g times qa of s. So I'll plug this expression from here into this expression so that h1 of s is removed from the earlier expression. So if I do that, that would be somewhat of this shape. This would give us the expression like this, that you have qi of s minus qa of s to be equal to a1 r over rho g, and you have s multiplied with qa of s. Now in this particular case, you can see that you have qa of s appearing over here as well as over here, so possibly you can combine the two, and for that matter you can say that this is going to be equal to qi of s to be equal to, you can take qa of s on the other side, and that would be making you take this qa of s common from there, and that would make this thing like 1 plus a1 r over rho g times s over here. Now in this particular scenario, I can make you kind of recall that this expression was defined to be equal to the capacitance of the tank, which was labeled corresponding to tank number 1 like C1, and I can use that obviously. So that would make this whole expression to be like this, that you have qi of s to be equal to qa of s, and then you have 1 plus c1 R S over here. So since you know that we need to transform this expression into a transfer function expression, which is output over input. So for that matter, since this is going to be output over input, let it be like x of s in a generic form. So this would mean that I can write down like output is qa, input is qi, and that would give me the expression like this, that this is going to be 1 over 1 plus C1 RS. So this expression can be plugged in the block diagram indicated over here. So I'm going to write that one down. So let's quickly do that. So this is going to be 1 over 1 plus C1 R of S. R multiplied with S to be precise. So this is going to be the transfer function corresponding to tag T1. Similarly, I can use these two expressions to come up with the transfer function corresponding to tag number 2, and that is going to be the output over input, which is in this case QB of S over QA of S, to be equal to, if you do that, this is going to come out to be equal to 1 plus C2 R into S. So this is going to be used in the block diagram at this place. And if I write it, this is going to be 1 over 1 plus C2 R into S, corresponding to tag 2. And this is going to give us how the output QB is originated or produced when given QA as the input, and internally the tag behaves according to this transfer function. And a similar exercise done for tag number 3 is going to produce a transfer function which produces the output QO over the input for this particular tag, which is QB, to be equal to 1 over 1 plus C3 times R times S. So this is going to be placed in this block, and if I write that one down, this is going to be equal to 1 over 1 plus C3 R into S, and this corresponds to tag 3, and this is going to produce the output Q out. And you can readily observe that we have transformed this 3 tag system into a block diagram, and without deriving the nth order differential equation for that. And you can now readily see that using the transfer function approach, I can find out the overall transfer function, and that would be the overall output, which is Q out over the input to the system, which is Qi, and that is going to be equal to Qa over Qi. Then you have Qb over Qa, then you have multiplied with that Q out over QB. So now you can obviously see that you can obviously cancel QA with QA over here, QB with QB, and that is going to be remaining like Q out over QI. But obviously you are now going to make use of the individual expressions, which is going to be 1 over 1 plus C1 R into S, multiplied with 1 over 1 plus C2 R into S multiplied with 1 over 1 plus C3 R into S. So this is going to be your overall transfer function, which is written in this form. One plus C2 R into S into 1 plus C3 R into S. So this is going to be the overall transfer function Q of S over Qi of S. As you can observe that this is the transfer function which contains three parts in it. This is the first, this as the second, and this as the third. And these three parts, when plotted on S-plane, are going to correspond to three poles. And to be precise, these poles are real poles, which means that on S-plane you are going to have the location of these poles on the real axis. So for that scenario, generally this is going to be possibly manifesting itself in three possible ways. For example, you can have the S-plane defined like this, that this is the real axis and this is the imaginary axis. And first possibility is that you have all these three poles to be coinciding one over each other. So this is going to be that you have a single location where three poles are placed. Now I'm assuming that you have the stable case. This means that all the poles are placed on the left half of the S-plane in this domain where you have the stable region. Now this is one of the possibility. The other possibility is that you have potentially two poles to be one over each other like this, and then you have one pole which is displaced from these two. It can be either on the left or on the right, but let it be like placed over there. So you have repeated poles over here, and this is the third pole. The third possibility in this particular case can be that you have all the three poles to be different from each other. So these are displaced from each other. So that can be a possibility, something like this, that you have 1, 2, and 3 poles of the system displaced. Now with this realization that this is the scenario where all the poles are placed on the real axis, that's why we are claiming this paradigm to be when you have three poles to be all real poles. Now when you have this transfer function the way it is being structured, kind of transformed into a more generic case, it would be something like you write this expression to be like this, that you have some gain k over these three parts as we have defined earlier, but now in a more generic case these would present themselves like 1 plus time constant 1 times s, 1 plus tau 2s, then 1 plus tau 3s. Now you can also kind of correlate with the expression that we have already written down over here, that C1, which is the capacitance of tank number 1 times the resistance of the valve connected to it, is actually going to correlate with the time constant with which the system is, or the tank is going to uh, provide the flow out of the tank. So similarly, over here C2 times R is going to be the time constant with which the tank number 2 is going to uh, uh, produce the output from itself. And similarly, the capacitance, which corresponds to tank number 3 times resistance of that particular valve, is going to correspond to tau 3. So this is the scenario where you have the more generic structure being shown over here, which we are going to use subsequently to come up with the solution using the Laplace transformations. So this can be the generic case. At this particular stage, I'll take one step back and discuss these third order systems, all having real poles with them, separately. And then I'm going to once again refer back to the example that we are discussing. So let's quickly discuss that. Third order systems with all real poles. So I can once again write this expression like g of s, which is the transfer function, as we have mentioned earlier. So this is going to be 1 plus tau 1 into s, then you have 1 plus tau 2s, then you have 1 plus tau 3s. Now, what I'm going to do, like in a stepwise fashion, manipulate this expression. So this is going to be, if I take tau 1s in the denominator, this is going to be k over tau 1, and then you have 1 over tau 1 plus s over here, and you have 1 plus tau 2s as it is already mentioned, and then you have 1 plus tau 3s over here. So similarly, I'm going to take tau 2 and tau 3 common from there. So this is going to be in that continuation something like this, that you have k over tau 1, tau 2 and tau 3, and then you have over here 1 plus tau 1 plus s, then you have 1 plus 1 over tau 2 plus s, and then you have 1 over tau 3 plus s in the denominator. So I'm going to do a little bit of modification now. I'm going to take these taus from here in the numerator. So when I do that, this is going to be somewhat of this shape: k over tau 1, tau 2 and tau 3 over, and I'm going to use a little modification like s first and then 1 over tau later. So this is going to be something like this. Similarly, the second term and the third term. Now this is what you can see, that this is the transfer function. Now if I now apply this transfer function in this fashion, that since this is defined to be equal to output over input, but if input is a unit step input, let's say, that would mean that x of s is going to be equal to 1 over s. So when I use that, that would mean that I can write one expression for y of s. So y of s is going to be equal to g of s times x of s, and that would be equal to this whole expression that we have written down already, all the three terms in the denominator, and then you have to multiply that with 1 over s. So if we do that, we are going to find this y of s to be equal to, I'm going to quickly write that one down, k over tau 1, tau 2, and tau 3 over s into s plus 1 over tau 1, and so on and so forth. Now, I'm going to now use the method of partial fractions to handle this algebraic expressions. I can say that in that particular case, y of s can be rewritten like in terms of having all those coefficients like a over s plus b over s plus 1 over tau 1 plus c over s plus 1 over tau 2, and similarly d over s plus 1 over tau 3. So as we are well aware that how we're going to find these coefficients a, b, c, and d, I'm not going to get into that detail, but once done, I'm going to assume that we can then take the inverse Laplace transform, and that when taken, you're going to have this transformed from the s domain back to the time domain, and that expression is going to be written down something like this: a plus this b e raised to power dependent on this minus t over tau 1, and similarly c e raised to power minus t over tau 2 plus d e raised to power minus t over tau 3. So this expression that we have now derived out of this whole activity is going to define how the system is going to behave in the time domain. Now let's try to map this expression onto a specific example. For this case, you have this expression mapped in this fashion that k is equal to 10 and tau 1 is equal to 1 and tau 2 to be equal to, let's say, 2, and tau 3 to be equal to 3, let's say. That would mean that you have the expression written to be something like this. Y of s would be equal to 10 by 6 over s into s plus 1, and then you have s plus 0.5, and then you have s plus 0.33. Let it be like that. So this would mean that you have one pole placed at minus 1, another pole placed at minus 0.5, and another pole placed at minus 0.33. And once you plug in these values and solve, eventually you are going to find a to be equal to 10, b would be equal to minus 5, and c would be equal to 40, and d would be equal to minus 45 after plugging in all these values. But in that particular case, you are going to observe that on an S-plane, where you have real and imaginary axis drawn. So this is the real axis and this is the imaginary axis. You are going to find out that if this is the -1 placed over here, you have one pole placed at this particular place. So this pole correlates with that. Another pole is placed at 0.5, which is going to be somewhat at this particular place. So you are going to place that pole over here. And then the third pole is at 0.33. So this would be somewhere closer to this point. So in this particular case, you can see that you have the poles placed in this fashion, that you have this as -1/1, which is -1 obviously, and -1/2 and -1/3. Now with this realization that you have these three poles all on the real axis, you can, depending upon the values of A, B, C and D, you can correlate that how those individual time responses are going to be added together, and that would look something like this. Let me use a different color. The one corresponding to this pole is going to look something like this, that you have starting from -5, if that's the case. Corresponding to B, you are going to have an exponential decay because it is much farther from the other two poles, so it is going to converge relatively quickly. Let me use black color from here. It is going to converge quickly. Something like this. And the second one, which corresponds to this location, is going to have a bit slower response. Let me try to map that as well. So this is the time axis. This was the time axis for the previous plot as well. But the second pole corresponds to C coefficient, which is starting from 40. So it is going to be somewhat placed somewhere over here. And it is going to be a bit slower than the previous decay. So this would look something like this. And the third one, which is going to have a pole placed at -0.33. So this is going to look something like this, that you have let me straighten it. So it is going to have -45 corresponding values. I'm going to kind of try to draw something like this. So -45 is somewhere over here. So it starts from here, and it with a decay which is even slower than the previous decays. So this is going to go like this. So in that particular case, actually what happens is that this response, the very first response over here, is going to be added with the second response, which is over here, and that is added with the third response, that is placed over here. And since we have a step response added as well, so that is going to be added as well. So this is going to be, because you have a to be equal to 10, so this is going to be somewhat like 10 is going to be here. So this response is going to be added in the mix in this fashion. So what is happening is that you have this as the first step response corresponding to this pole at the origin of the S-plane, and then you have another pole which is placed at uh, -1, which is going to be much quickly uh, converging to the uh, to the to the steady state value, but it will start from -5 because of this coefficient turning out to be -5, and then you have the third one, which is going to start from here, which is 40 value. Let me write that one down over here as well. So this is the 40 starting value. So it is going to converge, but a bit slow convergence than the convergence observed over here. And then the other pole, which is even closer to the origin of the S-plane, it is going to behave in a even slower fashion. So that is observed over here, and it starts from -45 because of this coefficient turning out to be -45 for this example. Now, in this particular scenario, you can see that uh, the time response and corresponding placement of the poles on the S-plane are very uh, interesting tools for a control engineer to look into the behavior of the system and see how those behaviors can be further improved. So although this is not the the topic of concern for us at this particular stage, but eventually when you're going to use these mathematical models in control systems, you are going to try to manipulate the behavior of the system by adding good controllers with them in order to further improve them. So all these responses that you are going to observe for the systems are needed to be further improved, and that is the quest in the control system paradigm. Now I'm going to try to place parametric values over here so that we can have specific solutions for this particular scenario. Let it be like A1 is equal to 2 meters square. Let A2 to be equal to 4 meters square. Let A3 to be even bigger, which is, let's say, 10 meters square. And let it be like rho, which is the density of the fluid, to be equal to 1 kilogram per meter cube. And let G to be equal to be simple, 10 meters per second square. And what else? We need the parametric value for R, which is constant for all the three valves that we have used. Let it be like you have 5 Newton second per meter raised to power 5. So let it be like that. And what else? I think we are good to go. We can use these parameters to find out what are going to be the capacitances C1, C2, and C3, and that is going to give us a specific a transfer function corresponding to these parametric values. And if you plug in all those values, this transfer function is going to become equal to 1 over 1 plus s. The second term is going to be 1 plus 2s. and the third term is going to be 1 plus 5s. Now obviously this is not the standard way of writing the transfer functions. We're going to kind of transform it into the standard form that we have derived for the generic case earlier. So I'm going to transform it into that, and once done, this is going to be equal to 0.1 over s plus 1, and you have s plus 0.5, and then you have s plus 0.2. So at this particular stage we have this expression which we are going to use in order to see how the output is going to be modeled. So let's do that in the next slide. So this Q out by Q in is written down already, 0.1 over s plus 1. You have s plus 0.5, and then you have s plus 0.2. Now if I place this Q in to be like a unit step, if it is unit step, that would mean that you have this to be equal to 1 over s added to the system. So that would mean that the output Q out in the s domain is equal to 0.1 over s into s plus 1, and the remaining terms are going to be as it is. Now once you have these written down, you can now transform using the partial fractions as we have done in earlier case as well. Once you apply that, you are going to write this expression to be equal to, in terms of having all those coefficients, which is a over s, the first one, then you have b over the first term, which is s plus 1, then you have c over the second term, which is s plus 0.5, then you have the third term, which is d, sorry, let me correct that, d over s plus 2, s plus 0.2. Now once you have those plugged in, you can say that this term, which is 0.1 over s into s plus 1 plus s plus 0.5, then into s plus 0.2, this whole expression is going to be equal to a multiplied with, other than s, all the other terms, which are going to be s plus 1. I'll quickly write those one down. You have seen this thing so many times, so I'll just quickly write those one down. Plus b, and then other than s plus 1 term, you're going to have all the other terms, which is s, you have s plus 0.5, then you have s plus 0.2. And similarly for c, other than s plus 0.5, you're going to have other terms, s, then you have s plus 1 and s plus 0.2. And similarly for d, you have s, and you have s plus 1, and you have s plus 0.5. This whole divided by the expression that we have already written down, And obviously you can equate the numerators, so that would mean that you have 0.1 to be equal to this whole expression. I'll quickly write that one down. Now if I can plug in the value of s to be equal to 0, this would give me one of the coefficients, so that would be 0.1 to be equal to a into 1, then you have 0.5, then you have 0.2. The other terms which are over here, because there is this s multiplied with this whole term, so this is going to be eliminated. Similarly this as well as this. So you're only left with this expression, which is going to give you the value of a, which turns out to be, let me use the consistent color, a to be equal to 0.1 divided by 0.5 divided by 0.2, which is going to be equal to 1. So this is one of the coefficients. Now similarly, you can have for s to be equal to -1, this would give that you have once again 0.1 to be equal to, and you have b multiplied with, because the term with a is automatically taken care of because you have -1 plus 1 0, eliminating the whole expression. So this is going to only have the b expression, so this is going to have b into -1, and then you have minus 0.5, and then you have minus 0.8. Now this would mean that you have b to be equal to, this would be minus 0.1 over 0.5 and 0.8. So this would be equal to minus 0.25 if I'm not wrong. So this is the second term. Similarly, for s to be equal to minus 0.5, which is the other term, you are going to find this whole expression to be 0.1 is equal to, the c expression is going to remain there, the others are going to be eliminated, so that's why it is going to be c into minus 0.5, then you have 0.5, and then you have minus 0.3. So this is going to give me something like c to be equal to 0.1 over 0.5 multiplied with 0.5 again, and you have 0.3. So this is going to give me, I suppose, something like 1.33, I suppose. Kindly counter check that. I think this is going to be the answer. Let me move on. So similarly, you are going to have the term when you have s to be equal to minus 0.2. So when you do that, this is going to give you the d value. So this is going to be 0.1, which is equal to d multiplied with 0.2 with a minus sign, obviously. And then you have something like 0.8, and then you have multiplied with that 0.3. So when you do that, this is going to give you d to be equal to 0.1 over, and let it be like with a minus sign because of minus 0.2, so divided by 0.2 into 0.8 into 0.3. So this is going to give me something like minus, I suppose it would be something like minus 2.1, I suppose. Kindly counter check that. So in that particular scenario, you are going to find out the expression of Q out to be equal to that particular scenario 1 over S, because A over S is going to be specifically structured like this. And you have minus 0.25 over S plus 1, and then you have plus 1.333 over S plus 0.5, and then you have added with that 2.1 over S plus 0.2. So this is going to be your expression after you have gone through the partial fractions and plugged in all those values of the coefficients A, B, C, and D. And now you can take the inverse Laplace transform, and that is going to give you Q out in the time domain now, and that's what we are interested in, to be equal to 1 minus 0.25 e raised to power minus t, and then you have plus 1.333 e raised to power minus 0.5 t, and with a, and if I'm not wrong, I've kind of used plus sign over here. Actually this is a minus sign, so with a minus 2.1 e raised to power minus 0.2 t. So that's what your flow equation, outflow equation, is going to be there when you have a three-tank system defined with those parameters that we have defined corresponding to areas of the tanks and the density of the fluid and the G and the resistance out of the valve. So with this realization that you have got this as the expression which defines the flow out from the output tank. And this would mean that you are going to have the S-plane constructed in this fashion. That you have the real axis, and similarly the imaginary axis. Now in this particular scenario, you can see that you have 3 poles corresponding to the system, and then there is another pole which is going to be at the origin of the S-plane because of the unit step given to the system. We are not going to get into that, but let's see the 3 poles corresponding to system. One is going to be because of this term, and obviously the coefficient for that is a -1, and another pole is going to be at -0.5, and the third pole is going to be at -0.2. So let's try to draw that on the S-plane. So if -1 is placed somewhere over here, one of the pole is going to be placed here, and using the same scale, 0.5 -0.5 is going to be somewhere over here, and so for that reason the second pole is going to be placed on the same real axis as well. The third pole is at -0.2, which is going to be somewhere over here, and that is where your third pole is placed. Now with this realization that you have all the three poles on the left hand side of the S-plane, you can say that since this belongs to the stable region, your system is going to behave in a stable fashion, or your system is going to be stable. And now I can see that how the time response is going to be added. So you have four terms, the first, second, third, and fourth terms. So let's try to see the very first term, how it is manifested. So let's try to draw that, and I'm going to use let's say a different color over here. So this term, when plotted, is going to have this arrangement. You have the time axis as the independent axis, and because it is going to be representing the unit step, so for that reason, if I use black color for that, you are going to have no response. But at t is equal to t naught, this is going to jump from that location to a value 1. So 1 is placed somewhere over here. So this is going to be one inference added in the system because of the input being given to it, like a unit step input. Let's try to see what happens with the second term. You can see that there is a coefficient of -0.25, so I can see that the system is going to, this component is going to start from -0.25, and then you can see that how it is decaying. So you have -1 as the decay rate. So with this realization, I'm going to draw another axis. So let's try to do that. Something like this, that you have the time axis. So if I try to draw it to the scale, -0.25 is somewhere over here, -0.25, and I'm going to use black color to indicate how it converges. So it converges really quick. Something like this. Now this is the second component corresponding to this term. So that is added in the system. So let's try to see what happens with the third term, which is with a positive sign, plus 1.333 e raised to power -0.5t. So if you compare the decay rate of this with the first that we have just drawn, so you can see that it is going to behave in a bit slower fashion. So in that particular scenario, let me try to draw that. Your system is going to behave somewhat in this fashion. You have the time axis, and if 1 is over here, 1.33 is going to be somewhere over here. So this is 1.333. So your system is going to, in this particular component, start from here and try to converge in somewhat this fashion. Because I'm drawing by hand, so obviously this is not going to be exactly like that, but actually this term is going to be a bit slower term than the term that we have drawn earlier over here. So let's move on and see what is going to happen with the last term, which is with a -2.1 coefficient. So this is going to behave in a similar fashion. Like you have time axis over here, you have the vertical axis, but now you're going to start. So this is going to be -1, this is going to be somewhat -2.1. So minus 2.1. So the system starts from here and it tries to converge, but with a slow rate, obviously, from the previous two behaviors. So this is going to somewhat take this shape. Now, with this realization that you have all the 4 individual components drawn on the system over here, you can say that the very first term, this, added with the second, added with the third, added with the fourth one, is going to have an accumulated response provided for the output Q naught. So that's why I'm going to place this plus sign between the two, between all the terms over there. So this is how the 3-tank system is going to behave. We have gone through all the details in a very careful fashion. We have seen how the transfer function is structured, and we have used the block diagram method to have all the individual blocks cascaded, and from there we wrote one transfer function, and then we solved it using the partial fraction method, and eventually reaching to the time domain expression. And then we have used the concepts of S-plane that we have explored along the way to see how the poles are going to be placed. And in a nutshell, we can see and we can observe that you have 3 poles. All the poles are placed on the left half of the S-plane, and all the poles are real as well. So that's why the response is going to be much simpler. But you are going to follow the same route when you have let's say complex conjugates available as well on the poles on the S-plane. But the route is going to be the same. You're going to use the partial fraction method once again, but your response is going to have oscillatory response added in the mix as well. So you can do that on your own, but the procedure would remain as it is. And obviously you can see that in this whole exercise we have observed in a very careful fashion what is the procedure, but most importantly we were more interested in what is going to be the response of the system when you have specific parameters given to it. So this is it for the example, and I think we have covered what we wanted to cover in this particular exercise, and that's why we're going to stop over here. So until next time, bye bye.